Good morning, good afternoon, good evening, ladies and gentlemen. Welcome to our presentation on thermodynamics. Thermodynamics. Yeah, thermodynamics is an area of engineering that's very important in our day-to-day lives. For instance, the cars you drive involve the laws of thermodynamics. The electricity you use in your homes, the generation of it, depends on the laws of thermodynamics. And there's so many other applications we're going to see as we go ahead. But the question that comes to our mind is, what is thermodynamics? Well, the word thermodynamics comes from two root words, two root Greek words. The first being thermos, which stands for heat, and the second being dynamis, which stands for power. And when we say power in engineering, power is usually described as the rate at which work is done. And what is work? Work is done when force moves through a distance. In other words, work is essentially mechanical motion. So if you pull this together, well, we say thermodynamics is a study of the relationship between heat and work. Heat and mechanical motion, which could also be converted into electricity, as we will see going forward. And then two new concepts are introduced here, heat and work. So we need to go a step further and define in clear terms what is heat and what is work. What is heat? Heat is energy in motion. I put here in bracket microscopic motion from one body or system to another because of temperature difference. Now, microscopic motion means that it is not observable with the eyes. When heat, for instance, if you have a hot object in contact with a cold object and heat flows from the hot object to the cold object, you can't visualize with your eyes, you can't see how the heat is flowing, but it's flowing microscopically. Heat is transferred, and there are three modes of heat transfer. There's conduction, convection, radiation. Now, this heat transfer occurs due to temperature difference. That heat flows from a region of higher temperature to a region of lower temperature, microscopically. Now, what is work? Work is mechanical motion, as we said earlier. When force F moves through a distance x in the direction of the force. Now, this motion is macroscopic. It involves physical displacement, movement that can be observed by the human eye. Movements of a material or body through a distance x due to force F. So unlike heat, where energy is transferred microscopically, there's no displacement of the body. but the energy flows from one body to the other while the two bodies retain their positions in space. In mechanical work, there is actual displacement of each point in the concerned bodies. For instance, if an electric motor is rotating, there's physical movement of each point in the rotor of the electric motor. When a conveyor belt is moving linearly, you can see the translational motion. Okay, so this is mechanical work. So, what are the key applications of thermodynamics? Well, one, conversion of heat to work. And that application is found in heat engines. For instance, any of the engines in your car, in your non-electric cars, fossil fuel powered cars, they work basically by the laws of thermodynamics, converting heat from combustion of fuel air mixtures into mechanical movements, which ultimately translate to the rotation of the car wheels and the motion of the car from point A to point B. So heat engine is a key application of the law of thermodynamics. Another key application is where we use work to move heat. We use work to move heat. For instance, in heat pumps, in refrigerators, and air conditioners. In this application, we use electricity to generate compression in compressors, compression of refrigerants in compressors, and that compression moves heat from a region of lower temperature to a region of higher temperature. So we're going to explain these in detail in our subsequent lectures. But for today, we focus on heat engines. So what is a heat engine? What is a heat engine? Well, I don't know, probably I should go to the slideshow mode. Should I? I think the slideshow mode should be okay. Okay, so what's a heat engine? A heat engine is a cyclic device that converts heat from a high temperature reservoir. So you can see here, it takes heat from a high temperature reservoir, converts it into mechanical motion or work, and then rejecting the residual heat to a low temperature reservoir. Now, in your petrol engine, for instance, the high temperature reservoir is called a source, will be the combustion chamber. Same for your diesel engine. Same for your gas turbine. Your gas engine, your natural gas engine, so on. Now, for your steam turbine, the high temperature reservoir or the source is a boiler that generates the steam. The steam, high pressure steam, turns the engine generating work, mechanical work that will in turn probably drive a generator to generate electricity. The residual heat from the process is discharged to the low temperature reservoir. In the case of this, the first four heat engines here will be the environment. For a steam turbine, it's usually the condenser discharges the residual heat, low temperature, low pressure steam. So the condenser, the cooling water condenses the steam, and you have hot water, and the hot water is then heated again in the boiler to produce steam again, which is then collected by the heat engine to generate work. And then the cyclic process continues, basically. So what does W drive? What does the work drive? Yeah, as we have said earlier, it could drive a vehicle. In the case of a petrol engine, diesel engine, gas engine, could drive a vehicle. It could also drive machinery. Now, most machinery today are electric motor driven. However, if you have a remote location or a place where electricity is not available, you could actually power your conveyor belts, your elevators, your whatever motive parts by a heat engine, basically. And you could also, of course, the obvious one is that the mechanical work or the shaft of your heat engine might be coupled to a generator, which is essentially an arrangement of electric coils and magnetic field such that a relative motion is generated between the coil and the field. And we know what happens when that happens. By Faraday's law of electromagnetic induction, EMF is induced in the coil, and so electricity is generated. So a heat engine basically converts heat from a high temperature reservoir into mechanical motion, which is subsequently used for different energy services such as vehicular movement, machinery movement, materials transfer, things like that. And of course, generation of electricity. Okay. Now, these are practical demonstrations of how heat engines work. Or how work is produced. How is work produced? Now, we say work is mechanical motion. And mechanical motion is when force is generated and moves a motive member through a distance in the direction of the force. To our left here, we see a petrol engine. To our right here, we see a gas turbine. Now, in this petrol engine, what happens? There's combustion of fuel-air mixture. The combustion makes the gas to expand. Expansion of the gas leads to linear motion, reciprocating kind of linear motion, and that motion is transmitted through the axle to the wheel, producing rotational motion in the wheel, which is again translated into rectilinear or linear motion of the car as the wheel rotates, basically. So you see that work is produced when there's controlled expansion of a heated gas in a confined space, the movable member. Now, the movable member here is a piston, isn't it? The piston moves as the gas, the airfoil mixture that has been combusted, as it expands due to combustion. Remember, by Charles' law, as the temperature of a gas, an ideal gas increases, the volume increases. So the volume increase is actually what we call expansion. And that expansion catalyzes a series of processes whereby linear motion is converted to rotational motion and then converted again to linear motion. Now, this is for the petrol engine case study. A similar thing happens in a gas turbine, where as the gas moves through the turbine blades, it expands. The expansion produces mechanical motion in the blades and in the whole system, the whole shaft system generally. So this is a snapshot in time of what happens in a petrol engine. To get a clear view, I will disengage from the slideshow mode and I'll see if I could stop the animation at some point. So let's stop. Let's stop at 1. So at point 1, there's intake of the fuel air mixture into the system. After the intake, what happens? At point 2, the inertia due to the motion of the wheel compresses the airfoil mixture. Then at the end of the compression, what happens? There's a release, there's a spark created by the spark plug, which leads to combustion. Now, in a petrol engine, that is required. In a diesel engine, the spark plug is not required due to the flash point of diesel is lower than that of petrol, basically. So the compression and then the combustion at the end of the compression stroke generates lots of heat, and that heat pushes down the piston. That causes the gas to expand, the gas of the airfoil mixture to expand, and then pushing down the piston. This is what we call the power stroke. The power stroke is when there's expansion of the gas, because that is expansion of the gas that does the work, basically, and that releases the power. And then at the end of the day, that power drives the car or drives whatever you are powering. And then the residual heat is then released at the exhaust phase. So let's look at the animation. Once again, we see that at the exhaust phase number 4, the brown residual heat is released. on this side. That's the exhaust stroke. Okay, we stop here for today. When we come next, we discuss heat engines in more detail, and then we do some example calculation problems. Until then, thanks for watching. Goodbye.